Hello everyone, welcome to my presentation. Thank you for being here. My name is Lam Nhi. With my partner is Nguyễn Thị Minh. Today we will talk about our project is brand recognition. The project focused on developing a mobile application for automatic species recognition within a university campus environment. The motivation stems from a desire to combine technology with nature education, allowing students and visitors to identify campuses for learning or recreational purpose. The primary goal is to build an image classification model that can accurately classify cheese species from photos taken on campus. The model should be efficient enough to run in real time on a mobile device. In our work, we use some techniques separable convolution, inception, and SE inception. Separable convolution is a type of convolution that splits the standard convolution into two steps. Stepwise convolution apply one filter per input channel to capture special feature. Pointwise convolution one by one combine information across channels. This greatly reduces computation and parameters compared to normal convolution, about 8 to 9 by less for 3 by 3 kernel. While keeping good accuracy is the core idea behind lightweight model like MobileNet. Inception is CNN architecture introduced in GoogleNet 2014, designed to capture multi-scale features efficiently. Instead of choosing one filter size 1 by 1, 3 by 3, 5 by 5, the inception module runs them in parallel along with pooling. The outputs are then concatenated, giving the network both size and cost feature. To reduce computation, one by one convolution are used before larger kernel to compress channel. SE inception combines the inception module with a squeeze and excitation SE block. Inception extract multi-scale feature 1 by 1, 3 by 3, 5 by 5 convolution plus pooling in parallel, then concatenated. SE block apply channel attention, squeeze global average, pooling to summarize each channel. Excitation fully connected layer learn channel weight, scale, reweight feature map by importance. The dataset used in this project was collected on our university campus, focusing on 6 common tree species present in the area. We aim to get about 100 images per species, resulting in a total dataset of approximately 600 images. The photos were taken using smartphone camera under various conditions on campus. Different trees of each species with variation in lighting, background, and angle. To capture a representative range of what a user might upload in the app, each image was labeled with its corresponding species. The 6 species constitute the classes for our classification module. Because the raw dataset was relatively small, 600 images is modeled for training a deep CNN. We apply several data augmentation techniques to artificially expand the training data and improve the model generalization. In each training epoch, images were randomly transformed with operations such as flipping, rotation, brightness, and contrast adjustment, zoom, and cropping. The augmentation operation ensures that the model doesn't overfit to specific position or lighting up place in the original photo. To get a sense of the dataset, feature distribution, and the separability of the classes, we perform an exploratory principal component analysis (BCA) on the image data. Finger below show a two-dimensional BCA scatter plot of the image with each front representing an image projected onto the first two principal components. Finger right side also shows a 3D BCA plot, first three components for the same data.
And next we'll come to the method. In our project, we use a MobileNet V3. The architecture is shown in the image. It is a inverted residual block with linear bottleneck. The process begins with a one-by-one convolution that increases the number of channels, thereby enriching the feature representation. It is followed by a depth-wise 3x3 convolution applied independently to each channel, which capture spatial features while keeping the computational cost low. To further enhance the representational power, a squeeze and excitation SE module is integrated. In this step, global average pooling compresses each channel into a single descriptor, which then passes through fully connected layers with ReLU and hard-sigmoid activations to learn channel-wise attention weights. These weights are used to rescale the feature maps, emphasizing informative channels while suppressing less relevant ones. Afterwards, a one-by-one convolution reduces the channel dimension back to a smaller size, forming a linear bottleneck that preserves essential information while minimizing redundancy. Finally, then the input and output dimensions are consistent. A skip connection is added, enabling residual learning and improving gradient flow during training. And you can see this is architecture of our model. You can see the table specification for MobileNet V3 small SE denote whether there is a squeeze and excite in that block. NL denote the type of non-linearity used. Here SS denote S width and RE denotes value, NBN denotes no bad normalization, and S denotes strong. And we'll come to the result. The training and validation curve in the mimic illustrate the learning process of the model throughout 100 epochs. As observed, both training and validation loss decrease sharply during the initial phase around the first 10 epochs, indicating that the model quickly learns meaningful features from the dataset. After approximately 20 epochs, the loss continues to decline and stabilize near zero. To getting good conversions through also a few spikes appear in the validation loss around epoch 5 and 20. The fluctuations are likely due to the small validation set or variations in sample difficulty which is common in limited datasets. And on the accuracy plot, both training and validation accuracies increase rapidly, surpassing 90% within the first few epochs. After around 30 epochs, the validation accuracy approaches 100% and remains stable with minimal fluctuation. The training accuracy follows a similar trend, steadily improving and eventually aligning closely with the validation curve. This demonstrates that the model is able to fit the data well and maintain strong generalization performance on unseen validation samples. The classification report demonstrates that the proposed model achieves strong and consistent performance across all key evaluation metrics. The overall accuracy of 95.44% indicates that the model correctly classifies the vast majority of test samples. Furthermore, the precision is slightly higher than RICO, suggesting that when the model predicts a given class, it is correct most of the time with very few false positives. The RICO 95.44% matches the accuracy value, reflecting that the model successfully captured nearly all relevant instances across the 6 species with very few false negatives. The F1 score of 95.43% with balanced precision and recall confirms that the model maintains high reliability in both identifying true positives and minimizing errors. The GradCam visualizations highlight that the model is effectively focusing on the most relevant regions of the images. In most cases, the heat maps emphasize the flowers or distinctive shapes, while less relevant areas such as the leaf or background receive lower attention. This indicates that the model is learning to attend to discriminative features that are likely important for classification. However, in some examples, the activation spreads partially to surrounding leaf or background regions, suggesting that the model may not be perfectly localized and could not still influenced by irrelevant information. Overall, the GradCam results provide good interpretability, showing that the model's predictions are generally guided by the correct reasons of interest. And this is a visualize a feature map in the intermediate layers. In this work, we successfully design and evaluate a MobileNet V3 small for plant recognition by using depth-wise separate convolutions, bottleneck layer, and squeezy and excitation modules. The model achieved a high level of efficiency without compromising accuracy. The experimental results demonstrate excellent performance across all key evaluation metrics with over 95% accuracy, precision, recall, and F1 score, validating the feasibility of real-time plant recognition on mobile platforms. Thank you for listening.